morning, everyone, and thank you for the very nice introduction, Greg. And really happy to be here at this event. As Greg mentioned, I'm from Harmony Desalting. We're a Boston-based startup working on better desalination technologies. Happy to be here. We're finding ourselves spending more time out west because this is really where the need is. So I was just in El Paso past couple of days, but finding ourselves spending time here. I think this is a great event. I'm a mechanical engineer by training, so I really appreciated the earlier talks from James and Wayne, learning about the hydrogeology, about creating rain. These are topics I don't know much about. What we're focused on at Harmony is really looking at the available water on the surface or below the surface that's gotten dirty and salty, and finding ways, cheaper ways to transform that water so that you can use it for drinking, irrigation, or industrial use. So today we're going to focus on, we think really the pieces are coming together where the ability to treat produced water, this is water that has gotten dirty from an oil and gas production process, take that water, treat it to the point where it can be reused beneficially in another application. And we think from a technological perspective, it's easy as 1, 2, 3. First step is better pre-treatment. So pre-treatment is all about pre-filters, taking that dirty water, taking out the oil and grease content so that you aren't going to clog up your reverse osmosis membranes. Reverse osmosis membranes will clog up real easily. That gets real expensive real fast, so really important to keep those membranes clean. There are a couple of advancements here. These are not companies that we are affiliated with, but we're seeing these innovations. And the first is a company, Polycera, out of UCLA in California. They've been in business well over a decade. And they've got an innovative membrane. They call it an organic metal membrane. And the key here is this membrane is oil resistant. So the oil is not sticking to that membrane. It's able to separate the oil from the water quite effectively. You can see on that right side, contact angles, oleophobicity, but basically the membranes don't stick to oil. Another company over on the East Coast, Massachusetts, Zwitterco out of Tufts University. This is a newer company, but they've been making a lot of progress very quickly, Zwitterco. Essentially, what these folks do is they coat membranes in a slippery surface. They're called Zwitter ions. Basically, there's a negative end and a positive end. And, again, basic concept is the membranes are super slippery, and anything that's fouling is not going to stick to the membranes. They've made a lot of headway. They've got commercial systems operating on landfill leachate, produced water, dairy industry, and they just launched a series of product lines. They are rapidly expanding. And these are just a couple examples. There's lots of other innovations, membranes that are able to be cleaned more effectively, which is really important. There's been advances in ceramic membranes. I'm highlighting these two because what I think is really cool, their membranes look just like what you might recognize reverse osmosis membranes. So these come in the form of a spiral wound element. They fit into standard pressure vessels. I think this is really powerful because any water treatment operator who knows reverse osmosis, it's going to be real easy for them to operate these systems. So that's the pre-treatment bit. Again, that's not our specialty, but if you're looking at treating produced water, definitely a necessary component. At Harmony, what we specialize in is a better reverse osmosis process. So this is technology that was developed in the lab at MIT it's been just over a decade now. We spun out about 4 years ago. Over the past 4 years, we've been focusing on deploying the technology in the field. Our very first demonstration, we went down to Yuma, Arizona, a contest sponsored by the Bureau of Reclamation, More Water, Less Concentrate, where we took home the grand prize, really showcasing our ability to resist scale formation. But Before I get too deep into that, this is a photo of a big reverse osmosis plant over by San Diego. Um, just by show of hands, who in the audience has a reverse osmosis system at their home? Curious. So good amount, maybe 30% of the audience. This is a really big reverse osmosis plant, but for anyone who's less familiar, I haven't had a chance to drive around here too much, but I imagine you all might have water kiosks around. If you've seen those if you use those water kiosks, if you've seen those around, those kiosks use the same reverse osmosis membranes you're seeing in this big plant over here. If you buy bottled water, whether it's the small bottles of water or big jugs, typically those are produced by reverse osmosis. Point I want to make here is reverse osmosis is an established, trusted technology, reliably produces drinkable water. Really, the challenges are in making the technology better, improving the energy consumption, improving the membrane fouling so that we can take reverse osmosis and treat more challenging waters. Reverse osmosis is easy if you're going to treat wastewater, tap water, or well water, but where the industry needs to go is expanding the capabilities of reverse osmosis, and that's what we're focused on. So first challenge we see in produced water due to the high salinities is energy consumption. So standard reverse osmosis uses a lot of energy. This energy requirement goes up as your salinity level goes up. And the way we think about it is conventional reverse osmosis. Most RO plants operate the same way as when RO was first invented in the 60s and 70s. And it basically operates like an open fire hydrant. It's a constant flow through process. You've got pressurized water coming in and you've got pressurized brine coming out. And this is really a big waste of energy. Some modern systems will have energy recovery devices to recover this energy, but that's another device that you've got to buy and maintain. And these devices aren't completely efficient. What we do, our innovation is to take reverse osmosis and reinvent it. We operate it as a batch process. So this is much more similar to how your espresso machine works. Basically, we're putting 100% of the pressurized flow towards the filter. And in this way, we're able to, this unlocks variable pressure operation. You've got variable salinity, variable pressure operation. Could go on and on about that, but the bottom line is our batch process is going to be the most energy efficient way to perform any desalination. Second big benefit comes down to the byproduct of desalination. So desalination is a separation process. You're taking an input of salty water and you're separating it into two streams, a freshwater stream and a concentrated brine stream. And hopefully you have a lot more of that freshwater than that concentrated brine. Brine, you got to do something with it. It's not going to disappear. You might haul it away. You might put it down an injection well, or you might dig an evaporation pond, like the one shown here. Where we see reverse osmosis going is all about reducing the size of the brine volume that you need to dispose of. But what limits this current technology is a phenomenon called scaling. So this is where you get crystallization of salts. These will clog the membranes. And what we do differently is we introduce a regular freshwater rinse. So we just got set up over at a shipyard up in Boston. That's where we're putting together our systems. I was talking to the owner and he was telling me about, he used to work on a crew that would sail across the Atlantic. And every day, first thing in the morning, first thing they would do is they had a water maker on board, and they would take that fresh water. First thing they would do is rinse off the hull. And that's to protect that paint job on that hull, because you got salt crystals in the water, in the air, that are going to attack that paint. And their captain prioritized that. That was the first job of the day, was to dissolve those crystals. Essentially, that's what we do with the membranes. Is we rinse the membranes, give those membranes a regular freshwater rinse, and keep them clean. And in doing so, we're able to recover more water and produce less brine. We've got our first produced water pilot anticipated to, these are photos from a site visit out in California. Lower TDS than the water you might find out in the Permian. We're looking at about 40,000 parts per million. This is a project funded by the Bureau of Reclamation in partnership with Active Membranes, another membrane, a membrane startup based in Southern California. But basically, we're going to combine our anti-scaling batch process with Active's anti-scaling batch membranes and really push the limits. Now, we're not claiming that there's going to be no limits with this in regards to scaling, but we know we can go further. We've shown that through our field demonstrations, and we're really looking to identify where the limits of where we can go with the water recovery and reduce that brine volume. So better RO is the core of what we do. But we have to go beyond RO, beyond this current state of RO, especially given Permian, you're seeing real high brine TDS, and we see a couple directions here. Namely, you're looking at taking membranes and operating them at higher pressures, and then also looking at something that's called low salt rejection RO. I've been calling it leaky RO more frequently. And again, higher TDS, higher salt content means scaling is going to be a concern. That's why we think batch desalting is the right fit here. But really the motivation here, when you get to really high brine concentrations, if you're looking to do a ZLD process, you're going to send your brine to a crystallizer or an evaporator. Basically, evaporate that water. That takes a lot of energy. That's really expensive. Using a membrane is always going to be cheaper. If you look back 50 years ago, most big desalination plants were thermal. Nowadays, membranes have taken over. So we're seeing this trend of pressure-driven membranes. They've taken over seawater desalination. We only see this continuing. So that's where we want to drive this technology. We're seeing it already. If you look at membranes, reverse osmosis membranes that were available 10 years ago, you were pretty much limited to 1,200 PSI. Today, there are membranes. DuPont, I believe, was the first, but a couple other manufacturers also provide these membranes. You're seeing pressure vessels and all the auxiliary equipment now available up to 1,800 PSI. This is 120 bar, up from 80 bar. And 10 years from now, we see this going up further, 200, maybe 300 bar, but basically extending the limitations of where you can operate a pressure-driven filtration process. One more thing we're doing is something called low salt rejection RO. So the idea here is basically if you don't need to produce drinkable water, you can use a leaky RO membrane. So the reason so much pressure is required is when you're trying to produce a stream that has basically zero salt content. So you can take, we're not the only ones doing this, but basically this idea is to lower the pressure difference required across the membrane and basically use these leaky RO membranes to concentrate brine while keeping the pressures low. This is a project we're getting ready to set up our first field pilot. This is a site, a 2-acre farm, city of Socorro, El Paso County. I was just there. Again, a project funded by the Bureau of Reclamation in partnership with a small farm there. As you can see, this is a 2-acre plot. The farmers here they have a saline well. Well TDS is about 2,500 parts per million. And you can see over in the lower left-hand corner, he is using this well water to grow some crops, but he's limited in what he's able to grow here. What he would really like to grow with this land is wine grapes. So this is what we're working towards, is we would set up a small desalting container on the lower left-hand side. That's a 20-foot container. It would produce about 4,000 gallons per day, totally solar powered, operating about a third of the day. but basically enable this farmer to use his land to grow wine grapes, fill that up, turn that dry, arid land into productive land, but kind of the real challenge is that brine pond. Brine pond needs to be permitted, designed, and constructed. I was just over there the past couple days trying to work through some of these logistics, but this is our shared vision. This is a pilot. It's a small farm. Probably not what makes sense looking long term. Probably want to look at larger systems moving forward. But we're really grateful to Bodega Loya. They've been really welcoming to us. They're really forward thinking. So trying to get this going. But this system is going to feature those leaky RO membranes I just mentioned, and that's what really enables this to become feasible. Without those leaky membranes, with a conventional RO system, you'd be looking at something more like this. So a brine pond that's much bigger and a system that's producing much less water. So looking at this doesn't really make sense, but we think we've got a solution: less brine, more water, have desalination, beneficial reuse, makes sense in a couple more places. So I talked a lot about technology, easy as 1, 2, 3. It's not that easy, but we think we have a lot of the pieces. We're working on putting them together, but we're finding, a lot of the challenges, some of the trickier things to sort out comes down to people, comes down to regulation, and comes down to education. So on Tuesday, I was at the planning and zoning meeting. City of Socorro, we're working on getting that property that I just showed you rezoned. They're adding back their agricultural designation and successfully got them to add in provisions for conditional use permits for small-scale desalination. Drawing a lot from TCEQ has pretty good guidance. Their permit for evaporation ponds, and they're basically relying on that for a lot of their own regulations. But a lot of what I find myself doing recently at this planning and zoning meeting is a lot of education. So showing people what do these evaporation ponds look like? What are the measures that are being taken to make sure that they're not going to pollute the environment? How do we know they're not going to overflow? When you're working on this stuff, for a long time, these things seem obvious, but you get people asking really basic questions. I think important to do more outreach and education. We've recently launched a public-facing website. I saw the weather modification group also has that. So this is something we're learning, doing a better job of. And then yesterday we held a hands-on demonstration. So again, a lot of these people, some people heard about this project. They were initially really concerned that they were against it. So we put together a small RO unit, flew it over there, set up a table, brought some snacks. We were there for about 4 hours last night, and really just showing people, what does this technology look like? Some education on real basic stuff. Conductivity readings. So we had different samples of water. What do these numbers mean? Is lower better? Is higher better? I think the technology is a big part of it, but really we're finding ourselves spending more and more time, talking with people, getting the community behind the project, and I think that is certainly going to be necessary for beneficial reuse of produced water. I know some folks here will be talking about that later in the afternoon. I know some people are working very hard on that around here and really appreciate that work. So with that, happy to take any questions and chat with you further. Thank you. Saw your hand go up first.
My questions are going to be in depth for me. I've treated fluids for 20 plus years all over the world. So out of curiosity, the pre-treatment process, starting essentially at the producer, right? You said separating crude and things like that nature. So after they get the crude and everything separated, would it be effective for your membranes in produced water? You visualizing West Texas, of course, in produced water. If you took the compounds that come out of your produced water and keep them from being complexed into major minerals, such as your calcium carbonate scales, sulfate binders, things of that nature, if you could keep those from precipitating before they ran into your membranes, would you be able to separate out more efficiently and your membranes not flooding near as fast?
Yeah, certainly to some extent, and some people, we've seen people use nanofiltration. Is one way to do that. You separate the divalents from the monovalents. But even if you knock out some of that scale-causing stuff earlier, our process is going to reconcentrate that stuff back up. So in the feed, there might not be scale-causing stuff, but our goal is to concentrate that stuff to the point where you start to get those salts in high enough concentrations where they are going to precipitate out.
Sure.
Yeah.
Okay.
But yeah, I think absolutely.
Because if you pre-treated, I was just curious if you pre-treated and the micron of the filtration process, is there a micron to it, or is it all just done by pressure?
No, there's a whole array of membranes. You got different pore sizes, different levels of size exclusion.
So if some of these were individually, so to speak, bonded or coated, each individual molecule, like your calcium is coated, it can't attach to anything else. Will there be a membrane that will capture your calcium and your iron compound, your magnesium compound? Because they're all different sizes and different molecular weights. So will each one of them be captured by chance?
I think this is something we should maybe talk about more offline after the presentation. Yeah, no, I'd love to chat more. Yeah, yep.
I appreciate that.
Yeah. Yes.
Well, just from the perspective of West Texas and the produced water, I got 3 questions. One, can you scale up to 80,000 milligrams per liter? You said you were working with 40,000. Second, the cost per barrel to do that, and then what percent is recovered of the produced water?
Right. Yeah. Real good question. So with conventional RO membranes, standard pressures, 80,000 is pretty much your limit. But with the high pressure membranes, so going up to 120 bar, you can push up just over 100,000 parts per million. And then if you combine our co-founder and CTO, she's a professor at a university in Germany. She's been doing a lot of work with ultra high pressure, low salt rejection ROs. So when you combine these two things, she's been able to reach concentrations of 170,000 milligrams per liter. So yeah, you can certainly take things further. We haven't done that yet in a field system, but we're working our way there.
And the second 2 questions, what's the cost per barrel?
Oh, right. Yes. Cost per barrel, I mean, depends on the system, depends on the size, but in the range of 10 to 30 cents per barrel.
Okay. And then what percent is recovered?
Yeah. So that, again, also depends specifically on the process, but we've shown, I think we can safely say we're going to recover more water than a conventional RO process. So for instance, our Yuma demonstration, conventional RO would recover 75% water. We took the brine and recovered 80% of that brine, pushing up the overall recovery in the neighborhood of 90, 93, 94% recovery. So that's our goal for all these systems, is push up the recovery. If you're at 50%, go up to 90%. If you're at in the 60s or 70s, go up to the mid 90s as high as possible. Great.
I have a question on our waters we're dealing with. What occurs with the radioactivity of these elements? Or they become a hazardous?
That's a really good question. I have to say, we have not had experience here yet, but generally speaking, the waste is leaving the process. So it's in contact with the membranes, but it ends up, for instance, in a brine pond. So I'd say if you're concentrating that radioactive material to the point where it needs to be specially handled, then you know, it's going to cost more to take care of that, certainly. But you will, I believe, be able to separate that from the fresh water. Yeah.
So we use your 80,000 parts as an example. What scalability do you have? Like how many barrels per day?
Right. Yeah, so I think the great thing about our process is we use standard desalination equipment. So in principle, we can scale up, you know, as much as you want. Where we are today, we have, as of this past July, we just commissioned a 40 gallon per minute, so about a barrel per minute, 200 cubes per day system out in Colorado. That's a research project with Colorado School of Mines and Purdue University. We're working our way up later this year to 1,000 cubes per day, about 200 barrels per minute. Yeah, all the equipment, you know, there's nothing stopping us from going further. It's just going to take some time. Thank you very much.